Basic concepts of stereochemistry. 1. Isomerism. Isomerism refers to the phenomenon where compounds share the same molecular formula but differ in their structural arrangements. There are two main types. 1. Structural isomers. These differ in the connectivity of atoms, e.g., butane versus isobutane. 2. Stereoisomers. These have the same connectivity but differ in the spatial arrangement of atoms. 2. Stereoisomers. Stereoisomers can be further classified into 1. Enantiomers. These are non-superimposable mirror images of each other, much like left and right hands. 1. Enantiomers exhibit optical activity, meaning they rotate plane polarized light in different directions. 2. Diastereomers. These are stereoisomers that are not mirror images of each other. 2. They can have different physical properties and reactivity. 3. Chirality. Chirality is a property of a molecule that makes it non-superimposable on its mirror image. A chiral molecule typically has at least one stereogenic center, often a carbon atom bonded to 4 different substituents. The configurations at these centers can be designated as R. rectus, or S. sinister, based on the Kahn-Ingold-Prelog priority rules. 4. Geometric isomerism. Geometric isomerism occurs due to restricted rotation around double bonds or within cyclic structures. This leads to 1. Cis isomers. Substituents are on the same side. This type of isomerism is commonly observed in alkenes and cyclic compounds. 5. Optical activity. Optical activity is a characteristic of chiral substances where they can rotate plane polarized light. The direction and degree of rotation depend on the specific enantiomer and its concentration. 6. Atroposomerism. Atroposomers are a type of stereoisomer resulting from hindered rotation around single bonds, often due to steric hindrance. This can lead to stable conformers that can be isolated. 7. Configurational versus conformational isomers. 1. Configurational isomers. These cannot be interconverted without breaking bonds, e.g., enantiomers. 2. Conformational isomers. These can be converted into one another by rotation around single bonds, e.g., different staggered and eclipsed forms of butane. 8. Lebel-Van Hoff rule. This rule states that for a molecule with NN stereogenic centers, there can be a maximum of 2 N2N stereoisomers possible. For example, D-glucose has 4 stereogenic centers, allowing for 24 equals 16 24 equals 16 possible stereoisomers. Importance of stereochemistry. Understanding stereochemistry is essential in fields such as drug design, where different stereoisomers can have vastly different biological effects. The thalidomide disaster illustrates this point. One enantiomer was effective as a sedative, while its mirror image caused severe birth defects. In summary, stereochemistry plays a vital role in determining the physical and chemical properties of molecules based on their three-dimensional arrangements. Understanding these concepts is crucial for chemists working in organic synthesis, pharmaceuticals, and materials science.